Here is something strange. An object can move at a perfectly constant speed and still be accelerating the entire time. A ball whirled on a string, the moon circling the Earth, a planet looping the sun. None of them speed up, yet every one of them accelerates. Today we uncover why and where the acceleration points. We now turn to a special class of motions. Motion in a plane about a central point. We call this central motion, and its most outstanding case is circular motion. Special cases like this one dominate the study of physics. The examples are everywhere. A bicycle rider on a circular track, a ball spun on a string, the rotation of a spinning wheel. Long before anyone understood gravity, early models described the planet moving in circles. The moon's path around the Earth is nearly circular. The planets trace nearly circular orbits around the sun. Even our own sun moves in a nearly circular orbit around the center of the galaxy, 50,000 light years from the massive black hole at its heart. Central motion is not only circular. When Newton solved the two-body problem for gravitational central force, he found the orbits can take four shapes: circular, elliptical, parabolic, or hyperbolic. Every one of them is still central force motion about the center of mass of the two bodies. And gravity is not the only central force. When an alpha particle, two protons and two neutrons bound as a helium nucleus, scatters off the nucleus of a gold atom, the electric or coulombic repulsion between them is also a central force, pushing along the line that joins their centers. Circular motion is the cleanest member of this much larger family. Let's describe the kinematics of circular motion: the position, the velocity, and the acceleration, treating it as a special case of two-dimensional motion. In straight-line motion, velocity and acceleration both point along the line of travel. Circular motion breaks that picture. As the object sweeps around the circle, its velocity is always tangent to the circle, pointing along the direction of travel at each instant. Picture cutting the string on a whirling ball. It flies off along the tangent, not along the radius. Here is the crucial consequence. Because the object keeps turning, the direction of that tangent is always changing, even when the speed never changes at all. A changing velocity means acceleration because acceleration is the rate of change of the velocity vector, and the vector changes if either its length or its direction changes. So where does this acceleration point? Take the velocity arrow at one instant and the velocity arrow a moment later, and subtract them. The little arrow that bridges their tips is the change in velocity. When we examine this carefully, that change points toward the center of the circle, so there must be a non-zero component of acceleration directed radially inward toward the center. This inward acceleration has a name. We call it the centripetal acceleration, from the Latin for center seeking. But the centripetal piece is not always the whole story. If the object is also speeding up or slowing down, then its speed is changing too, and that adds a second piece of acceleration. This piece is tangential. It points along the direction of motion, in line with the velocity, speeding the object up or slowing it down. So in general, the acceleration splits into two perpendicular parts. The tangential part changes how fast you go. The centripetal part changes which way you go. Now here is the clean special case. When the object moves at constant speed around the circle, the tangential part vanishes, and only the centripetal acceleration remains, pointing steadily inward. Newton saw the deepest version of this idea early. In 1666, 20 years before he published the Principia, he realized that the moon is always falling toward the center of the Earth. That sounds impossible since the moon never gets closer. But think about his first law. With no force at all, the moon would simply coast in a straight line, flying off on a tangent and leaving us forever. Instead, it curves into a closed orbit. Something must be continuously bending its straight line path inward. That bending is the falling. The moon is perpetually falling toward Earth, yet perpetually missing it. An inward acceleration demands an inward force. Whenever an object is constrained to move in a circle, there must be a force acting on it directed toward the center. We call it the centripetal force, a radial force pointing inward, and it is what produces the centripetal acceleration. Now make it quantitative. Newton's second law is a vector equation, so it holds component by component. Take its radial component, the part pointing along the radius toward the center. The radial force equals the mass times the radial acceleration. In symbols, F sub r equals m times a sub r. Force inward, acceleration inward, tied together by the mass. Step back and see the whole logic. In circular motion, the velocity rides tangent to the circle, so its direction is forever changing, even at unchanging speed. A changing velocity is an acceleration, and that acceleration points inward, the centripetal acceleration. Speeding up or slowing down adds a tangential piece, but constant speed leaves the inward acceleration alone. And by Newton's second law, that inward acceleration means an inward force, the centripetal force. From here, we can build the rest, angular velocity, period, and exactly how big that inward pull must be. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.